Okay, so I'm here and I'm gonna do an experiment with my brother. We're gonna look at rotational motion, and the first thing we're gonna look at, well, like the only thing we're gonna look at, is rotational inertia of an extended object. So my brother here is gonna rotate this ball with his body serving as the axis of rotation, and we're gonna use the longest radius first, and we're gonna see how difficult it is to rotate or angularly accelerate the ball. Go. Okay, so next we're gonna use a shorter radius, so it's gonna be smaller in length. So let's go and let's rotate the ball. Okay, was that easier or harder?
Easier.
It was easier, right? Okay, now we're gonna do it even closer. So now we want to angularly accelerate this ball. Remember, we're looking at rotational inertia, so spin it. Was that easier or harder?
Easier.
Okay, so it looks like as we decrease the radius, it's going to become easier and easier to spin the ball, or rotate it, or angularly accelerate it. This is part 2 of examining rotational inertia. So this time, we're going to focus on the mass of the extended object. Last time we looked at the radius, or the distance from the center of rotation, the axis of rotation. So my brother here is going to model this. Hopefully he can do it. So ready? Wait, try to grab it in the middle. So now try to angularly accelerate it. So like, see? Go the other way. Is it difficult or easy?
It's difficult.
Okay, so here we have a lot of mass. We have attached the mass to the end of the barbell. So now take off the mass. Okay, I'm gonna help. Okay, we're back for the second part of the second part. So now you're gonna try to rotate it without the weights. Is it harder or easier?
Easier.
So we removed the masses, so the ends have less mass. So we're gonna treat this as an extended object, even though like it's pretty bent and stuff. So we didn't change the radius here. All we did was change the mass. So what we're looking at is rotational inertia, and later we're gonna view how we can represent this algebraically. Okay, we're back with another experiment, and we're gonna be analyzing the moment of inertia. We're gonna look at the two components, which are mass and radius. So we're gonna look at how not only the radius or the mass, but how the distribution of the mass affects the moment of inertia or the rotational inertia. So in this experiment, we're gonna roll these two weights down an incline, or an incline of sorts. So we have two weights. They have different masses or weights. So this is 10 pounds, and then this is 10 kilograms, which is around 22 pounds. So we're gonna roll both of them down this incline, and we're gonna compare the rates of rotation. So we're gonna see how readily these two objects are gonna rotate. So here's our first object. So it's nice and smooth. So now we have our next object with considerably more mass. It's more massive. So from the same line, right? Start from the same line with the same initial speed or velocity. And we're gonna see how this rotates. It doesn't rotate as readily. So we can actually do a race. Let's see how we can do a race. So, okay, before we go on to the next experiment, I wanted to take a look at the equation for the moment of inertia. And what we just looked at was mass. So I'm gonna circle mass, and I'm gonna see what kind of relationship the mass has with the moment of inertia. So just by looking at this, I see that the mass and the moment of inertia have a direct relationship. There's a direct proportion between them. So if I increase the mass, I'm going to increase the moment of inertia. And that's true empirically or physically. We observed that that was the case. The moment of inertia, when it was greater, produced a smaller acceleration or rate of rotation. Okay, before we looked at mass, but now we're going to look at specifically the distribution of the mass, or how radially far the masses are positioned or concentrated. So here we have two objects of the same mass or the same weight, but we see that this object is way larger and this object is way smaller. So the masses here are more concentrated toward the center or axis of rotation, while here we're going to have masses that is farther away. So we're going to see how readily these two rotate, and by that we're going to really compare the effect of the rotational inertia. So we're going to rotate the bigger object, the larger object, first with the same initial speed. We see that's how it rotates. Now we're going to rotate the smaller object with the same initial speed. Okay, so now let's race the two. So we're gonna, while he's doing that, I'm going to take a look at my board, which shows the equation for the moment of inertia. So it's saying that between the moment of inertia and the mass, there is a direct proportion. If I increase the mass, I'm going to increase the moment of inertia. And we're going to see why this is significant. But right now we're going to focus on the radius. So from this equation, we see that the moment of inertia is directly proportional to the square of the radius. So we know that mass and its distribution have an effect on the moment of inertia. So let's race these two objects. So at the same time, let's see if this is feasible. Okay, that did not work out well. But anyway, we have the previous experiment. Okay, in this part, I really wanted to put everything together. So I know that we already viewed the equation for the moment of inertia, right? Where we see that there is a direct proportion between the moment of inertia and the radius squared. But why do we care about moment of inertia? And why have I mentioned angular acceleration so often, or the rate of rotation so often? It's because of this. Well, let's take a look at Newton's second law, which says that the acceleration is equal to the force, or the net force, over the mass. And through this, we know that the mass is inversely proportional to the acceleration. So more mass for the same force, it's going to produce a smaller acceleration. And we come to think of this as inertia. So the greater the inertia of an object, or the more massive an object is, it has a greater inertia, and therefore it's harder to move the object. It's harder to change the object's velocity to produce an acceleration, which we know is a change in velocity over a change in time. But how can we relate this to rotation? Well, we know that the net torque, I'm writing it here, is equal to the moment of inertia times alpha. I alpha, that is moment of inertia times the angular acceleration. So I can rewrite this expression if you allow me to erase this with my shirt. I know, very low budget thing to do, but it has to be done. I can say that the angular acceleration is equal to the moment, the torque, is equal to the torque, the net torque, over the moment of inertia. So the angular acceleration is inversely proportional to the moment of inertia. So when I increase the moment of inertia of the objects that we looked at, I saw that the rate of rotation, or the difficulty of rotating the object, became increased. It was exacerbated. And that's because if I have a larger moment of inertia, then I'm going to have a very small angular acceleration. I can represent it that way, where I can make this the 1 over, and then this is the A. It's just showing that there is an inverse proportion. And my angular acceleration, what it represents is just like any other kinematic variable. It represents the change in the angular velocity over the change in time. And we know that the angular velocity is the change in angular displacement over the change in time. So this really has an effect on all these kinematic variables. If I have a smaller acceleration, I am going to produce a smaller change in angular velocity, right? And these are all interconnected. So the rate that I'm going through that angle is going to be much smaller because the time it takes, right? We have to look at equations. Equations tell us everything. They're beautiful. If this rate of angular velocity, not the rate of the angular displacement actually, is smaller, then we know that time has to increase. So it takes much longer. You require much more pull and push to really go through the same angle. So that's why it's much smaller. We just think of time. It's really hard. You know, like when you're moving a large box, well, that's translational, right? It's going to probably take a lot more force or a lot more time to push that box. So I hope this explanation makes sense. It's pretty extemporaneous or off the cuff, but I love rotation, and I hope I'm explaining it to the best of my ability.